Okay, good morning. Week 6, Friday. The agenda we're going to do today is unsymmetry shear loading. We're going to continue. Okay, so last time where we stopped is we look at unsymmetrical loading. Okay, so if we quickly recap on Wednesday what went on. So in unsymmetrical loading, you have a structure as can be seen on figure 6.42 that when you put a load acting exactly at the centroid. C is the centroid about both the y and z axis. Okay, the structure is going to induce a twist. Okay, I repeat again, the structure is going to induce a twist. So on figure 6.41, I explained why a twist, because on the right hand side of the structure relative to the applied force V, the structure is less rigid. So it tends to want to rotate in the right hand side. Okay, so what we're trying to do over here, not me, but what we're trying to do, okay, in terms of the structure analysis, we try to use the same equation, i.e. shear stress is equal to BQ divided by IT. Okay, but this equation over here, or the shear flow, which is VQ over I, is only valid when there is what? No twisting. Okay, when there's no twisting. So the only way to be able to apply the same formula, okay, is to do an offset, E over here, as you can see. And E is what we call a shear center. Okay, E is what we call, the distance E is the shift to induce the counter moment. O is known as the shear center. Okay, so why is it towards, why E is towards the left? Okay, relative to point C. So if I were to draw point C, okay, so this is our point C over here, right? Then I draw, okay, this is our point C. This is because we're going to induce a what? A counter moment. Okay, we're going to. So when you induce a counter moment by applying Newton's third law, action equal reaction, same magnitude, opposite direction, you eliminate the what? The twist. You get rid of the twist. So once you get rid of the twist, we go back to be able to apply the same equation over here. Okay, so that's where we last finish off. Now, so today, what we're going to do? Okay, we're going to do the math. It's quite straightforward. It's quite easy. So before I go on, okay, I want you to look on figure 6.45. Now all these figure on Avenue to Learn is on Wednesday's notes. Okay, all these figures are there. So this is where we have to design our forces working within the structure. Okay, so the first thing you have to do is there are two types of forces. As you can see, you have the F. Okay, you have the V over here. Okay, so now I know you used to see Vy, Vz. This is just V. Okay, so F or V denotes the shear flow or the shear force acting on the vertical member. Okay, vertical member through the centroid. Okay, so the centroid axis is going to be here. Okay, so you have one along X, 1 along the Y. Okay, sorry, Z and Y. Then you have F. Okay, we have F and F prime, which is the shear force acting on the horizontal member or vertical member away from the centroid. Okay. So now we are going to design the shear force flow direction. Okay. So from this case, right, we know that we have a shear force coming down vertically, Vy. Okay. So we know that we are going to induce a twist. Okay. So this is where we have to design our shear force. Okay. So the shear force is also the same with our shear flow. The web controls the direction. Okay. Still the same thing. By the way, it is from looking at unsymmetrical shear in how they analyze. That's where I also teach you how to design the shear flow in where in thin wall analysis, okay, and also in non-thin wall. Okay, so we design the shear flow over here. We design the shear force. Okay, so again the web controls. That's why the flow is in that direction. Okay, so if Vy, I'm going to draw. So if Vy is or V is coming in this direction, this will going towards the left, and the top part it will be going, sorry, the bottom one will be going towards the right, the top member will be going to the left, and these are also known as your terminal now. Okay, these are known as your terminal now. So what these forces are going to induce, okay, they are the one that are going to induce the counter moment, because at this present moment, if Vy is exactly acting on the centroid point C, the structure will tend to twist this way. Okay. So we need to induce a counter moment, right? We induce a counter. So the only way to induce a counter moment is we offset our shear force V, okay, and at a distance E. Okay, so this will induce our counter moment or counter twist or moment, whatever you want to call it. Okay, so now we are going to determine E. Okay, so I'm going to take this diagram again. I'm going to copy if I could. No, that's not allowed. Okay, I'm going to zoom out. Right, then I'm going to draw a point now. Okay, so I'm going to look at, I want you to look at this diagram. I'm going to draw our centroid. I'm going to draw a centroid. So this is our point C. Okay, that is our point C. Then I'm going to impose, this is our F, right? And this over here is our V within the structure. Okay, and these are our terminal. Okay, So we are going to determine the distance E. Okay, which is the distance between point C to, I'm going to call this O, okay, to O, which is the shear center. Okay, so I'm going to draw our transformation Y, Z. This is our rotation in the X. Okay, so we're going to take moment. So I mentioned about moment about the x-axis, and we're going to take the moment at point C. The whole thing is equal to 0. Okay, so we know the distance from this is a straightforward part. Okay, the distance from here to here is h/2, and likewise for the one below, this is also h/2. Okay, so the top one, the F, right? So we're going to take moment of point C. Moment is force multiplied by perpendicular distance. Is going anti-clockwise. So F multiplied by h/2. So this is for the top F plus by F that's below the centroid h/2. Okay. And then we know that we have also plus V multiplied by E. Okay. So is this V we are talking about now? Okay. And this thing is equal to 0. So when you get over here, the next step is V multiplied by E is equal to FH. Sorry, minus FH. And finally, E is equal to minus FH by B. Okay, and it's because if you look at E, for this case, E going toward the left-hand side is always negative. All right, so note E is going towards the left relative to point C. Therefore, it is what? Negative. Okay. So the equation then become E is equal to FH over V. Okay. We drop the negative because both are negatives. Okay. So this is a formula. Very straightforward formula. Okay. Nothing difficult, nothing complex. I'm looking at the chat to see is there any question. I don't hear any question. Anyone, any question so far? So,
sorry, Eugene, this is just the formula for this specific shape though, right?
it's Marco, it's a general formula that we're going to apply for unsymmetrical shear.
Oh, okay.
Okay, it's a generic formula that always stands. Okay, Marco. Right. So now the thing is, how do we determine F? Okay, how do we determine F? So to determine F, there are two ways to determine. Okay, so to determine F, okay, between 2 points. Okay, so let's say between point A to point B. Okay, so point A to point B means this point A. Hold on, yeah, I think I can do this. It means this is our point A. This is our point B. Okay, so this is determined by you can use two form. Okay, you can use a shear flow Q multiplied by ds.